Welcome, everyone. I'm David Hyndman, Dean of the School of Natural Sciences and Mathematics here at the University of Texas at Dallas. UT Dallas is the largest public university in the Dallas area. It was initially founded as a private research arm of Texas Instruments. In 1962, a group of distinguished scientists arrived in North Dallas to undertake an ambitious experiment to build a community of scholars in the Southwest to conduct fundamental research and provide graduate education in science and mathematics. The Graduate Research Center of the Southwest and its research arm, the Southwest Center for Advanced Studies, received this charter from Texas in 1961, spurred into creation by Eric Johnson, Cecil Green, and Eugene McDermott, the founders of Texas Instruments. The institution became the University of Texas at Dallas in 1969. As such, we're among the youngest universities around. Less than 47 years after our founding, the Carnegie Foundation designated UT Dallas as a doctoral research university with highest research activity, faster than any other school in Texas. UT Dallas is associated with 4 Nobel Prizes and has members of the National Academies of Science and Engineering on its faculty. Among prominent research projects are those in the areas of space science and nanotechnology. Notable NSM faculty, staff, and alumni include an Antarctic explorer, an astronaut, 2 university presidents, and a founder of the world's first molecular nanotechnology company. The university's rise in stature and recognition started right here in natural sciences and mathematics. And part of its reputation stands from work and contributions of the late Dr. Wolfgang Rindler. Rindler was a founding member of the school's mathematical physics division. A dedicated and highly praised teacher, he was instrumental not only in establishment of the Department of Physics, but also the rise of scientific research at the university. In a career that spanned more than 60 years, Rindler was one of the most prominent experts in theoretical relativistic cosmology and general relativity, areas of research that deal with the origin, evolution, and structure of the universe. Sadly, he passed away in 2019. Among Rindler's lasting contributions are the establishment of the Texas Symposium on Relativistic Astrophysics. It started out in 1963 and has continued on roughly every 2 years all around the world. Rindler also authored and co-authored 7 books, advanced the study of cosmology and general relativity, igniting the imaginations of thousands of students. His studies of the universe, how it moves, and how Albert Einstein's theories apply are cited worldwide. One textbook, titled Spinors and Space Time, was written in collaboration with today's guest. Sir Roger Penrose, a friend and collaborator of Rindler, is a British mathematical physicist who in the 1960s formulated many of the basic features of black holes. He is the Emeritus Rouse Ball Professor of Mathematics at the University of Oxford and an Emeritus Fellow of Wadham College at Oxford. He's also a Fellow of the Royal Society, an international member of the US National Academy of Sciences, and a recipient of numerous awards, including the 1988 Wolf Foundation Prize in Physics, which he shared with Dr. Stephen Hawking. Penrose recently was the co-winner of the 2020 Nobel Prize in Physics for his discovery that black holes are a direct consequence of Albert Einstein's general theory of relativity, which describes gravity. Black holes are supermassive but compact regions in space, where space and time are distorted and gravity is so strong that nothing escapes. Today, he'll share some details from his 25-year collaboration with the late Dr. Wolfgang Rindler. If you have questions during or after the presentation, please type them into the chat. We will then select questions that will be read to Dr. Penrose. With that introduction, it is my pleasure to introduce you to Sir Roger Penrose.
It's a great honor and a pleasure for me to pay my respects to Wolfgang Rindler, because we had a long collaboration, starting, I think, when I was at King's College, London, when Wolfgang was there. This would, I think, have been in 1961. I had been in the US for a couple of years previous to that. I just come back to England, and I went to King's College, and I think I shared an office with Wolfgang at that time. And I think I gave a talk, a seminar or something, on using spinors in general relativity. And Wolfgang was found interested in this, and we decided that we would write some mimeograph notes, I think it was, to try and express the ideas that I'd been talking about and try and develop them. These things grew and grew until we got in touch with the Cambridge University Press, and they were interested and decided that we made a contract with them to write this book, which we called Spinors and Space Time. Here we see the book. As it turned out, it was 2 books because it just grew and grew and grew. And we decided eventually, rather reluctantly, that we had to split it in 2. One of the big problems I remember about splitting it in 2 was that a lot of things in what we were doing in the latter part of the book, we had to refer back to the earlier part of the book. And so we needed an initial introductory section which contained all the information that we needed to refer to. That seemed to work. I think I seem to remember going through all the equations that were needed and for the second volume 2, and strung that together and made a sort of connected account, which was the beginning of volume 2, which sort of summarized what happened in volume 1. Anyway, let me just see what, yes. I should explain that I had been interested in spinors previously, and I'll talk about that, I think, as the lecture goes on. I had been interested in general relativity for quite some while. I went to lectures by Hermann Bondi when I was in Cambridge as a graduate student, and also by Paul Dirac. And I learned some quantum mechanics from him and from Bondi general relativity. I was doing pure mathematics previously to that, and some of that influence I'll come to in a moment. But let me move on to the next picture, which is basically to show in space-time, you see, we have 4 dimensions, and this represents 3 spatial arrows. You can see the 3 arrows sort of horizontally. That's meant to be in the space directions. And then you have a time arrow there. So you have 4 axes to describe what's going on in space-time. Now here I have a picture which is taken from the book, which shows in the middle, you see the light cone, and time is progressing upwards. And the horizontal planes, the lowest one is an earlier time, and then this is time now, if you like, the middle one, and then a later time there. And you can see that this represents the history of this light cone, where you have a sphere. Of course, you have to imagine that there's an extra dimension involved, and you see the extra dimension indicated at the right, so that when it looks like a circle, the bottom, that's really a sphere. So you have to get used to the idea that I can't just illustrate all the dimensions, and you sometimes have to throw away a dimension in order to make it fit on the picture. So here we have yesterday, if you like, here we have today, and there we have tomorrow. And this is the null cone or light cone of a point in the middle of today. And you can see the future light rays pointing out. These are, if you like, think of them as photons traveling out from that point. The history of them would be this cone. Okay, well, let's move on to the next picture. This is what I want to illustrate. You see, go back to the previous picture. When you see a sphere, I've indicated the sphere as pointing, you see, imagine yourself sitting in the middle of this picture, and the light rays coming into your eye, the history of them are these generators of this inward cone. So each one of these light rays coming into your eye represents a single point on the celestial sphere. So the sphere I'm indicating at the right-hand side represents the sky. So you're looking out at the sky, every point on the sky represents, if you like, a photon coming in, and this is the space-time picture of that photon coming in like this. So there's one point, and that would be this one, another point would be that. I'll often talk about the future cone rather than the past cone, but they're both in this picture. So the light rays coming in, each of those rays is a point in the past cone, and the ones going out, each is a point in the future cone. Now you see, this is a sphere, but you have to bear in mind that it's not really metrically a sphere, because if you look at the same sky and you're moving at a certain speed, so suppose you're not sort of stationary in the picture, like staying put would be this horizontal line here, but suppose you're moving at some speed and you look out at the same sky, that same sky would look somewhat distorted. So you have to imagine that the points are displaced into the direction you're moving. It would really look as though the sky was sort of squashed in the direction you're moving along in the direction of these arrows. But an important point about this squashing, this distortion of the sky, is that it's what's called conformal. So that it's not really a distortion. If you had a circular pattern, suppose there was a pattern of stars in the sky, which happened to make a little circle, then even though they would be displaced in the direction you're moving, they would still remain circular. That's what's meant by conformal. I feel like angles on the sky would still be the same angle no matter how you're moving. So although the celestial sky wouldn't look like the same metric sphere, it's squashed in the direction you're moving and stretched out in the direction you're moving from. Nevertheless, it would be a conformal map in the sense that angles are preserved in this map, or little circles are preserved. And that's an important point, which we'll come to shortly. Now here I think of a stereographic projection, and this is an important thing to understand if we're thinking about conformal structures. So you imagine that is the sky, if you like, this celestial sphere, and I'm taking a projection of that from the North Pole onto an equatorial plane. And the thing about this projection is it also is conformal. So if you have little circles in the sky here, they would be little circles in this plane. Now this plane I'm thinking of, and this is an important thing, I'm thinking of this plane often as a complex plane. So this, when I say complex plane, so it's the Argon plane or the Bessel plane, a point in that plane represents a complex number. So you think of the real axis as being this horizontal line here, that represents real numbers, but the reside at right angles to that within the plane would represent the multiples of the square root of -1, multiples of I, and the entire plane represents the complex numbers. So you have a real part and an imaginary part. And it's very useful to talk in these terms. And when we talk about spinors, as I shall shortly, they are complex objects. I was always interested in that because quantum mechanics depends on complex numbers. The whole structure of quantum mechanics is really depends on complex numbers. People think of it as probabilities, but the probabilities are really the squares of the amplitudes of the complex number. So they're the square of the distance from the origin of the complex number. I'm not going to talk about quantum mechanics, but I was always interested in describing things in terms of complex numbers because it seemed to indicate a connection with quantum mechanics. And you can see this very much when you talk about spin. I'm really not going to talk about these features here, but nevertheless, let's keep this picture in mind because it tells you how this celestial sphere can be mapped in a conformal way to this complex plane. So you can think of each point on the sphere as being represented by a complex number. The one exception would be the North Pole, because the North Pole, if you try and project it from the North Pole, you just go shooting off to infinity. So the North Pole is represented by infinity in this plane. So you fold up the plane with one point at infinity, and that gives you this Riemann sphere, as it's sometimes called. Okay, let me move on. And now I have a picture here of a spinor. So this is what we're going to be talking about. The book that we wrote together, called Spinors and Space Time, was a description of this notion of a spinor and how it can be used to describe the geometry of space-time in surprising ways, often very revealing ways that you don't see easily without using spinor methods. Now, here we have on the right-hand side of the picture, well, you see here a light ray joining to the origin, this point P, and that sort of represents a spinor, not quite. There's a little bit more to it. You see, it's not just this light ray, it's a vector too. So you have to think of a vector starting at that point. So it's got a length, if you like. Well, not really a length, but a certain extent from that point. And in addition, there's a little flag at the end of it. So you see the little flag, that represents the whole spinor. So the spinor is represented by this vector, if you like. It's called a null vector, and the little flag plane. So the flag is orthogonal to the line here. Well, one way of thinking about that flag plane is, let's go to the left-hand side of the picture. The direction from the origin of this flagpole, so there's a flagpole to the spinor and a flag plane. The flagpole is represented by this point on the celestial sphere. So that's a point on the sky, if you like. And that's one point there. And the flag plane represents a little arrow. So you can see a little arrow at that point. That little arrow gives you the direction of that plane. And the whole thing is needed in order to describe a spinor. Now, this is what's called a two-component spinor. That's because it's got two complex numbers to describe it. So it's two complex numbers, and they're enough to define the spinor. And it gives you a point on the sphere. That's basically the ratio of the complex numbers, which gives you the celestial sphere. And the additional aspect to this is the flag plane and the sort of how long that vector is. So it's the vector itself, that is to say, not just the direction of it, but the vector itself, and also the little flag plane, which gives you a little direction on the sphere. Now that's not quite a spinor. Well, there's one other very curious feature it has, because if you rotate this flag plane around the flagpole, in other words, if you take this little arrow here and rotate it round on the sphere, by the time you've gone all the way around back to where it started, the spinor has changed into its negative. Now, this is a very curious feature, and it came from the discovery of the spin of the electron. Particles of spin half, such as an electron or a proton, they are described by these things called spinors. And this was why they were called spinors, because they describe the spin of an electron or a proton. Now, in this next picture here, I'm also showing that the little flag plane, this I don't show him. This is just the stereographic projection. I think we had this before. Yes, sorry, I meant to be moving in the other direction. Here's the spinor. Yes, now what is curious about the spinor? Well, here's that, just showing you how the flag plane, that's what I was meaning to show you. The little flag plane is given by a little arrow on this celestial sphere. And so as you project it down, you get a little arrow on the plane. So that's another way of thinking about how to characterize the spinor. And sometimes I'll talk about the flag planes as arrows on this plane. Now, the curious thing about a spinor is illustrated here. This is what's called Dirac's scissor problem. And I'm going to show the top version, which is the way he described it. I think it was a little joke on his part, because you imagine this string looped backwards and forwards through the handle of the scissors here, and it goes around the chair and comes back like this. Now, the thing is, if you rotate the scissors right the way around for 360 degrees, these strings all got twisted up. And I'm going to imagine that you try to untwist them, keeping the chair fixed, keeping the scissors fixed, and just moving the strings around. There's no way of untwisting it. So it's a sort of different state once you've gone all the way around. But let's go around twice. So you go all the way around and all the way around again. So 720 degrees, not 360, twice round. And the Dirac scissors problem is, now, can you undo the strings? And yes, you can. What you have to do basically is to loop it around the scissors. I think the joke was that if you get frustrated, you just cut the string, the other scissors. But that's, of course, here's a version of it which is a little more obvious, which is instead of using the strings, you have a belt. And as you twist twice round, the belt gets twisted. And by looping the belt round the scissors, you can undo the twist. You can undo two twists, but not one. So you have to imagine for a spinner that there are these sort of imaginary strings or something connecting it to the outside world. And once you go all the way around once, twist it round, rotate it through 360 degrees, it's still not where it was before because these connections with the outside world are still there. But if you go once round again, then the connections with the outside world can be undone. So a spinner is something which when you rotate all the way around 360 degrees, all the way around once, it becomes different from itself. When you go all the way around again, it goes back to itself. In fact, it's called minus itself. You say it becomes its negative once you go all the way around once. And that's the feature of a spinner. So you have to bear that in mind, that although my picture is pretty well an accurate picture of a spinner, so this picture is accurate only if you think of it as a spinorial object. That is, if you take the flag plane, go all the way around twice, it's back where it was. Only if you go all the way around once, it's negative, the spinner. So that's the thing you have to bear in mind. The spinner is not quite geometrical in the ordinary sense of the thing there that you can see, but it's spinorially geometrical. That is, if you rotate it once completely all the way around, it becomes minus itself all the way around again, and it gets back to itself. Okay, so that is the picture of a spinner. And that's the one I had before. Let me move up now to that's the Dirac spinners. Now here I'm showing you how you connect the components of a spinner with the, well, if you like, a frame. I've got here slightly curiously arranged, but for a good reason. The time axis, space-time axis is pointing upward. So that's T, that's the time axis. Then we have three space axes, X, Y, and Z, X, Y, and Z, if you like, pointing spatially. So this little cube represents the space directions, and you have three directions there. Now, for the spinner, you have what's called a spin frame. Now, the spin frame consists of two particular spinners. I've painted one of them white and one of them black. This one I tend to call Omicron, and the second one is iota. So the iota one is the black one, and the micron one is the white one. And that gives you a basis. You can choose a different basis. You could choose a different pair if you like. But this particular one is related in this canonical way to with the flag planes pointing in this way. So you can have the Omicron one points in the Z direction or the Z direction, and the iota one points in the minus Z direction, and the flag plane points along the x-axis here. So that's a sort of canonical way you can set up a coordinate frame for the spinners and relate it to the space-time. So it's a very specific geometrical thing. Okay, now here I want to show you something rather curious about spinners. There are lots of things about spinners which curiously come up much easier to do with spinners than to do with ordinary vectors and things like that. There are lots of other things which are more difficult to do. And it's curious which ones are easy and which ones are difficult. I'm going to show you something which is a little difficult, rather curiously enough. If you've got vectors in ordinary space, you see here I have two vectors, this one u, this lower arrow, and the other one v. And you can imagine these vectors being added together. This is the normal way of adding vectors. What you do is you make a parallelogram, and the diagonal of that parallelogram gives you the sum, u plus v. So it's a very geometrical idea, this adding together vectors, and this is very familiar to people. So the sum of vectors is just given by the parallelogram rule. But what about spinners? What is the sum of two spinners? So if I have two spinners represented by their flag planes, if I go back, how would I do it? Well, I'll give you the answer. It's a rather curious answer. And here is the answer. You see, these are the flagpoles. Let's suppose two of them I'm adding together to the one which represented by OR, the one represented by OP. And these are the flag planes of two spinners. And let me try and add those together. Now, what the sum of those two would be, it would be another one, OQ, where if I imagine the endpoints of the flagpoles, here are these two flagpoles, and this is the sum of the two, these will always form an equilateral triangle. So they always form an equilateral triangle. That doesn't give you a complete answer because you need to know where the flag planes are. And they're given in this way. You see, let's imagine, going back to the previous picture, suppose you take the plane of this equilateral triangle and regard that as simultaneous. Then the time direction is sort of orthogonal to that. The time direction, which makes them simultaneous, I'm using that as my rest frame. Now, if I do that, then I look at the three flag planes, and they're little arrows. And what you find is that for the sum of them, I've got sort of kappa is 1, omega is 1, and kappa plus omega is the sum. You just rotate. You'll find they lie in a circle, and you rotate them around, and it's like this. Now, you see, you might think it's rather curious because it looks as though the sum is on equal footing with all the others. Well, that's because you can't tell whether it's that or minus that, because you have to know whether it's just the geometrical location of that flag plane doesn't tell you whether that's the spinor or minus the spinor. So you have to be careful about that. And you can track that by just following things around. I won't go into the details of that. You see, it really is symmetrical because, see, kappa and omega and minus kappa plus omega, they satisfy the fact that the sum of all three is 0. And so that is a symmetrical relationship. So the fact that the geometry looks symmetrical is only because of this curious minus sign, because they're spinorial objects. It's a little bit confusing, and I'm not really going into the details to sort it out. I just tried to show you that there is a geometrical way of representing the sum of spinors, but it's a bit confusing and complicated. So it's not the sort of thing you want to do. So there are other things which I'll try and show you, which are the kind of thing you would much more want to do. Now, let me talk about one of the reasons I was interested in spinors initially. Here we have the first, the first real observation of confirming general relativity, which was, here's the sun, that's the sun's disk, and you imagine it's an eclipse of the sun, so you can see the stars, and then the sun's gravitational field, the light passing by the sun gets bent, and so it looks as though the sun magnifies, if you like, the field of vision, and that pushes outwards the star. So if the star would have been here, if it weren't for the sun, when the sun is there, the image is displaced outwards. Now, this displacement outwards is less and less the further you go away, whereas so that means that the diameter along the direction as you're going out from the width along the direction as you're going outwards is going to get less. So it gets squashed, and it's stretched outwards because it moves out. So the diameter in the other direction gets stretched. So what would look like a little circle becomes an ellipse. So the celestial sphere gets distorted by the presence of the sun's gravitational field. And this is a direct measure of the gravitational field in a form which is the curvature, that form of the curvature which is directly the gravitational field. And I'll come to this a bit later, but a space-time picture of what's going on is this here. So here's an observer looking back, and what you see is this distortion part, because the sun's gravitational field has caused what would have been a circular image to be an elliptical image. And that means that the light rays, as they go past the sun, gets distorted. And this distortion effect is due to what's called the Weyl part of the curvature of space-time. The other part of the curvature of space-time is what's called the Ricci part. And this is a straightforward focusing inwards. The Weyl part is the distortion. And it's very useful to split the curvature into these two forms, because Einstein's equations directly tell you that the Weyl part, it's the Ricci part, it's this other part, the focusing inwards part, is directly given by the matter distribution, or the matter density flux across your light ray. And that gives you the positive lens effect. Whereas the Weyl part is a pure astigmatism. It's the distortion part. And this is the gravitational field, the free gravitational field, if you like. And this is the part due to the matter directly. Okay, now the curvature of space-time. You see, Einstein had this wonderful idea of describing gravity in terms of a curved space. It was a wonderful idea, and it incorporates this amazing insight due to Galileo that you can get rid of a field, a gravitational field, by falling freely in it. You imagine Galileo's experiment, or not whether he actually did it or not, it's another question, but he imagined somebody dropping objects from the Leaning Tower of Pisa, and as they fall, the gravitational field seems to disappear. So if you imagine two rocks, a big rock and a little rock, and there might be a little insect sitting on the big rock, and it looks as to the insect that the gravitational field has gone. The little rock seems to be hovering. Well, when it hits the ground, of course, it's a different story. But as it falls freely, the gravitational field has disappeared. So in a certain sense, you can make gravity disappear by falling freely. And that's the basic idea of Einstein's general relativity. Can you make somehow the effect, which is not the falling freely, is not really what the gravitational field is in a sense. It's the deviation from uniformity. And the deviation from uniformity is the curvature. And the curvature of space-time is the gravitational field. Now, it's a nice idea, very beautiful, amazing idea, but it wouldn't have got anywhere if it hadn't been for an amazing piece of work, which was started basically, well, Gauss a little bit, but primarily this man. This is Bernhard Riemann, who basically founded the subject of differential geometry or curved space-times, or curved spaces, I should say, not space-times. Higher dimensions, there could be any number of dimensions. Gauss had looked at it in 2 dimensions, but it's much more complicated situation when you have more than 2 dimensions. And you have to have a thing called the curvature tensor, which is called the Riemann tensor, after Mr. Riemann. And the Riemann tensor describes the curvature of space-time. Now, it's a tensor. Now, the thing is that in order to talk about general relativity or any other curved more than 2-dimensional space-time, you need to know these things called tensors. And so Riemann really started off this notion of tensors. And they are complicated objects. And one of the things that's complicated about them, you write them down, they've got lots of indices like this. I've got one here, which has got 3 indices. And each one of these indices runs over the number of dimensions of the space. So if there would be 3 values of A, if you like, if it was 3-dimensional space, or 4 if it was 4-dimensional space-time, and then the B would take 3 possible values. So if we've got 3 of them, you'd be 4 times 4 times 4 would be the number of numbers encapsulated in this T thing. So a tensor's got lots and lots of components to it, all these different numbers, where you take the different values of A, B, and C. So it's a collection of numbers like that. And sometimes they're upstairs, sometimes they're downstairs. These are called contravariant of the upstairs and covariant downstairs. I won't go into the differences. The ones that sort of vector-like are the upstairs ones. The ones that sort of density-like are the downstairs ones, in a certain sense. Now, there's a certain operation. You can add these things together if you've got the indices and the right sort of structure the same. You can add them together. Or you can multiply them together and they just get bigger and bigger and bigger with more and more components. You just multiply all of this different ways around. But there's a way of making things smaller again, which is a thing called contraction. And contraction happens when you sum over, I've got at the bottom a sum sign. You put one of the indices at the top equal to one of the indices at the bottom, and then you add together whatever they are. You see, if it's an n-dimensional space, then you n different numbers. So you've got to add those n different numbers together. And that's called contraction. And this is a very important operation. So you can add them, you can multiply them up, or you can contract them down again. And this is the basic algebra of tensors. It's really quite complicated. And Einstein had to get used to the idea in order to understand his own theory. And he had to have it explained to him. Now, you see, Einstein introduced a certain idea, which is called the Summation Convention. And what you do, he noticed, really, that whenever you've got these sums here, that it's because you've got an upstairs index and a downstairs index, and you make them equal, and then you sum over the equal numbers. So if the top one is a 3 and the bottom one's a 3, you add that one. If the top one was a 2 and the bottom one was 2, you add that one. So you add them all up together. So Einstein noticed when you do this a lot and lots of times, you get loads and loads of these sums, these sigma signs, which tell you to add them up. And that's an awful lot of writing down things. And you don't need to put that thing down because whenever you see a repeated index like this, you're supposed to add them up. That's the rule. So Einstein said, let's not just get rid of the symbols, and it makes it look a lot simpler. Now, it's a curious thing because a lot of mathematicians hated this, you see. They said, look, this is sloppy. We don't like that. And they always put the symbols in. Physicists don't. They like to leave the symbols out. And they don't mind being a little sloppy, if you like. But they knew what they were doing, and they're perfectly happy with this thing called the Summation Convention, that the sigma signs are always there. And you just have to imagine you're doing the sum. And if you work anything out explicitly, you've got to do the sum. But you chase down you've got to be careful not to have 3 letters the same, because then you've got to have only 2. You've got to make sure your numbers, your letters don't start repeating themselves too many times. One up and one down, then that means adding them together, but you mustn't have them 2 at once apart from that. Okay, that's the Einstein Summation Convention. All very complicated. Now you see, I introduced this notion of abstract indices. Now this notion, I should explain that we do, in the book with Wolfgang Rindler, we use these abstract indices. Now, so often people say, well, if you're a physicist, you say, well, what's the point? We know what we're doing. When I say abstract indices, I mean that these little letters you write on the tensors, if you like, you think of them as not really representing collections of numbers. They're just a thing which is keeping track. If it was a vector, you say, you just keep a vector. You say the vector, and you might put the index A if you want its components. But if you want the vector thing, you don't write the indices. But then you can't keep track of things if you don't write the indices. So what I say is, you do write the indices, but you don't think of them as lots of numbers. You just think of them as a thing. Now, you see, when I was doing my graduate student work, I was playing with things in algebraic geometry, which involved very complicated tensors. And I got the feeling, well, look, I'm not very good at lots and lots of tiny indices. I can barely see them. I would much rather like to draw diagrams. And these are the diagrams here. Imagine the first one is a tensor with 2 up indices and 2 bottom indices. And instead of writing the little letters, I just write lines. The lines go up if they're the top ones, they go down if they're the bottom ones. And here I have another one, you see. And I might have a disembodied line. That means a thing called the Kronecker delta, which more or less doesn't do anything. Or you might have upstairs vectors and covectors when they're coming down. And you make an expression. Here I made an expression. Sometimes they cross over. And if you had the letters there, you'd write if it was an A and a C, you'd write as a C and an A, whatever it was, you see. But instead of writing that and looking very carefully at where the letters are, you write the diagrams. You make sure that each piece of the diagram, you add bits together like this. Each piece of the diagram has to have the ends of the lines in a corresponding spot. So each time they're corresponding. But these would be the letters if you want to introduce the letters, and you would introduce them. So you put A, B, C or something like that. But it's much easier to think about the diagrams. At least I find it much easier. And you could see what's going without having a microscope to see when the letters were the same and when they're not. You just follow the lines. And you can join them up. Here you see, here's a contraction. This is when I've joined it up. That means the letter on this object here would have been the same letter as on there. So instead of just having the lines being loose, they join up. So you can represent the contractions by having the loops like that. So I find this a much nicer way of representing things. So that was the, now I'll just show you a few examples. You can have the disembodied lines. They're kind of handy, you see, because they represent permutations and things like this. And it's a very nice way of representing permutations by crossing these things over in complicated ways. I'm not going to follow these things in details. I just want to give you an impression of sort of things. And you sometimes add them together. You have symmetrizers or anti-symmetrizers. And here there's probably these. The wiggly line, in my case, meant you add them all up. The straight line means you add or subtract. Depends on whether it's an even permutation or an odd one. And to see whether it's even or odd, you just count the number of crossings of the lines. If they cross an odd number of times, that means you put a minus sign. If they cross an even number of times, it means you have a plus sign. So that's a very nice way of keeping track of all these things that are going on. I'm not going to go on with all these things, but here you can see some contractions at the bottom. We have loops. And if you contract a line onto itself, it gives you the dimension of the space. That's a nice thing. When you have a closed loop, it gives you the dimension of the space. I like to play around with these things sometimes when they were purely abstract and they didn't have components at all. And they had to be abstract because sometimes when you contract the thing onto itself, you get a negative number. And that means the number of dimensions is negative. But you can still have these algebras, these sort of abstract tensor algebras, even when the dimensions seemed like a negative number. And they were quite useful, these things. That's not what I want to talk about here, but I thought I'd give you some impression of the kinds of things you can do with the abstract things. Now, an important thing with tensors is you want to be able to differentiate them. That is to say, how they change as you move around. And the differentiation is represented by a loop. So I have a little loop going around the thing, and that means, and the loop always has a leg attached to it, and that means it's what's called covariant derivative. If you know differential geometry, you'll know what I mean by that. But these loops, and you have loops, and then you sort of skew symmetrizing by putting the cross line across, and then you get the curvatures. So the curvatures come out, and this little funny thing here is meant to be a Riemann tensor. So you have these Riemann tensors coming out when you take the loops and you skew symmetrize about them. And it's a nice way of representing these things. I find the diagrams much easier to work with than lots and lots of indices. I had students, and some of them were good at doing this, and some of them got better than I was. Some of them didn't get the hang of them at all. It depends on whether you like diagrams or not. Anyway, that's that picture. In fact, these now are the Riemann tensors. So I had this particular notation for the Riemann curvature tensor. The R stands for the Riemann curvature tensor. It has 4 of these indices, so it's got lots and lots of components. So the curvatures in different directions can be quite complicated. And then you've got the loop means you put the metric in. So there's a thing called the metric, which tells you distances between things, times between things. And that is conveniently represented by a little loop. And the Riemann tensor has a nice lot of symmetries of complicated things, which are represented here. I'm not going to go into that, but it's a very nice way of representing them. Okay, spinors. Now, what do spinors do for you? Now, you see, I had a lot of trouble because I had this understanding of tensors and the diagrams and all that. And then I heard about spinors, and I went to Dirac's lectures, and he described about spinors. And when I went to his lectures, they suddenly became clear. I was trying to read books that my colleague and mentor, Dennis Sharma, had told me to read and understand about the spinors, and I found them very difficult. But Dirac's lectures on these things absolutely made it clear to me. And the answer is really as following, or going back to the lines here. What you imagine is that if you take a microscope and you look carefully at one of these lines, you see it's really 2 lines together, sitting really right close together. And those 2 lines, if you keep them together as one thing, you're playing with tensors. But if you're allowed to split the hair, if you like, take them apart and exchange them with another one, then you're really doing spinors. So the spinors are really taking the magnifying glass to the lines and seeing that they're really double in a certain sense. Now, what that means in terms of the abstract letters, and this is really very helpful. You see, remember that the letter A, or the letter B, or the letter C, the little letter, represented an index. So when it has a line, that was this little line. But when you make them spinors, that's a pair of lattices. So the little single index becomes a pair. And since one was tending to use little letters for the tensor indices, you can, there's actually a thing here which I always regretted. There was a time somewhat earlier than this when I think it was John Wheeler and Misner and Thorne were writing their great Bible, whatever it is, on gravitation. And they wanted to have a systematic notation for when you use Greek letters and Latin letters and so on. And they wrote around to all sorts of people and say, what do you use? Would you like to use Latin or Greek? And I said, I didn't say anything. I was just too slow at getting back to them. I never responded. And I kept kicking myself because most people said, oh, well, we'll use Greek letters for the tensor indices. Now, you see, that's no good to me because I want to have a way of saying when you've got the tensor and when you've got the spinor. And if you have either a small letter or a big letter, then I can tell which is which. But if it's Greek letters, well, I very rapidly run out of capital Greek letters before they don't look like Greeks anymore. How do I know a big A from a big alpha? You see, and things like that. So I really don't use the Greek letters for the tensor indices for this reason. But unfortunately, I think a majority of people do the other, and that makes this kind of notation very confusing to them, which is a great shame. I don't know whether they would have, whether writing from a letter from me would have made them change their minds about Greek letters, but to me, it was the wrong choice because using Latin letters means there's always a straight translation. If it's a little a, you use a capital A. If it's a little b, you use a capital B. And it's either A without a prime or with a prime. People used to use dots, but then I remember the paper I was writing, the editor wrote, telephone me or something, we can't use little dots on the capital letters. How about primes? So I said, okay, use primes. In fact, I got quite to like the primes because they're a little bit easier on the eye than the dots. And they separate out the pairs nicely, which is quite nice. Anyway, why do I use one without the dot? Well, you see, there are two kinds of spinors, really. There are the spinors which have just the ordinary spinors, and then there are complex conjugate spinors. See, if you remember the complex plane and you've got the square root of -1, the thing which with complex conjugate is when you change, you see the square root of -1 is called I, but then there's another square root of -1, which is -I. And you have to know whether you're using I or -I. And if you've got an expression and you want to change all your I's to -I's, that's called the complex conjugate. And that's a useful notion to have. But if you like, it's a different world when you go over to the complex conjugates. So the spinors, you either have them with the unprime or the dual spinors, or the conjugate spinors, I'll call them, and you have the other one. So the complex conjugate of a spinor is one with a primed index. So you have one of each kind. It's the ordinary spinor and the complex conjugate spinor. And you multiply them together like this, and you get this index. And so all the indices, and here I've got the metric, you see. Here is the metric of space-time. It's got two indices, G, A, B, and this is what people like to write down. And well, they like to write G alpha beta, you see, but it doesn't work for me. GAB is the metric. That tells you distances between things. It tells you times elapsed between things. With us, I'm really infinitesimal. If you're looking at them very close together, it tells you the time and the time lapse or the space distance at very close points. Now, what happens when the spinors, each A becomes an A and an A prime, each B becomes a B and a B prime, and it splits down the middle. You get one thing, and then that's the amazing thing about it. It splits down the middle, and you get these little epsilons. The thing about it, which is slightly awkward, but you have to live with it, is that with the A and the B, it's symmetrical. If you swap them around, GAB is equal to GBA. So it's the same as it is one way around as the other. But with the spinors, it changes sign. So if I put AB, if I put BA, that would be minus epsilon AB. So that's a bit of a nuisance. You've got to keep track of the signs all the time. Other ways of doing that, but it's an irritation. But apart from that, these epsilons are really simpler things than G's. And so they really are very simple objects. Now, this is what you do. You have a tensor expression. You replace all the A's with A prime, BB. Of course, if you just did that, you get just twice as many indices, and that doesn't simplify anything. But what you find is that very often you can swap around the indices individually without, you see, as I said before, you could swap the A and the B without the big A and the bigger B, the spinors, without swapping around the little a and the little b. And that does something non-trivial. So it looks trivial in the spinors, but it's non-trivial with the tensors. Okay, so let me move now to the next one here. Now I've got a notation, a diagrammatic notation for the spinors, and I have to have them sloping one way or the other, depending on whether they've got the primes or the not primes. So I slope them one way for primed indices and slope the other for the other. Sometimes I don't bother about that, but it's useful to keep track of. Okay, now we have the, I won't go into the details of it, but I'll just show it. You can keep track of the signs very nicely with these simple rules. But if you have a zigzag which doesn't cross, you have a plus sign. If it does cross, you get a minus sign. And it makes everything work nicely. I won't go into the details. I just wanted to show you the pictures. Now, this is the amazing thing. Here we take the Riemann tensor. This is the full curvature of a space-time. And then you write it in spinors. And of course, you have twice as many indices. But now it splits up into this very nice lot of things. The two at the top are, remember I talked about the Weyl curvature and the Ricci curvature. The two at the top are the Weyl curvature. And it's much nicer writing it this way than in tensors, because when you write the Weyl curvature in tensors, it's a great complicated mess of a thing. And it's the Weyl curvature tells you the distortion. It also tells you the gravitational field directly. I think it's good to have an analogy here with Maxwell theory. See, Maxwell described the electromagnetic field. It was an amazing achievement. Faraday had done his experiments, and then Maxwell fitted it all together and deduced from these equations that there would be propagation of electromagnetic fields through space which traveled with the speed of light. In fact, it was light, or I should say the other way around. Light is electromagnetic fields, and this comes out of these amazing equations of Maxwell. Now, Maxwell's equations have this splitting in a similar sort of way. You've got a bit, which is, you see, look at these sides here. All the indices are the same kind. They haven't got primes on them, or they have all got primes. Not only that, but they're completely symmetrical. So these are complete, rather than having the very complicated Weyl thing, which has got symmetries and asymmetries, you've got the things which represent the Weyl thing in spinors, which is a very beautiful, highly symmetrical thing. The rest of the stuff is what comes from the matter. So the analogy with Maxwell is this is the field, gravitational waves are waves in the Weyl curvature. Maxwell field is the waves in the electromagnetic field. But then there's also in Maxwell theory the source, which is what's called the charge current vector. And so you've got the field, which is the analog of that is the psi things here. And the analog of the source, that's the source of the field, that would be what's called the charge current vector. And you have a very similar splitting. There's a little difference in the differential order of difference, but it's very similar apart from that. That you've got two more indices. You've got 4 instead of 2. And if you do the spinors for Maxwell's equations, you've got a thing with 2 indices, which is completely symmetrical. So it brings out the analogy and the differences as well between electromagnetic and gravitational radiation. Now, here we see this is the Weyl curvature. Now, if I wrote this in tensors, it would be a complicated mess. But if I write it in spinors, it's just got these 2 pieces. One is the left-handed part, and the other is the right-handed part. And that's the C minus and C plus, if you like. And the left-handed part is takes the psi, and the other is the complex conjugate of psi. And this completely symmetrical thing has a lot of beautiful features. When I first hit on this, I realized that it had to have this property, that it always splits into 4 single spinors. The round brackets mean it's symmetrized. So you have to write down all the possible A, B, C, Ds in all the possible different ways. But it's roughly, to make it symmetrical, you've got to do that because this is symmetrical. So that has to be. But apart from that, it's just 4 spinors. So you have the four spinors, which give you four directions along the right, four flagpoles, if you like. So that a general spinor, you've got four flagpoles, and they might coincide in different ways, and that gives you a nice classification. And it's a very beautiful way of understanding how these different kinds of gravitational fields can behave. If you're looking at the field of a spherically symmetrical mass, like the sun, if you think of the sun as a spherically symmetrical body, then there's the Schwarzschild solution, which is the first solution of Einstein's equations, found shortly after Einstein found his equations. And this describes the gravitational field of a spherical body, very closely describes the field of the sun. And in that case, you see two of them the same, alpha and beta the same, and gamma and delta the same. So you've just got what's called 2-2 structure. And the source of a black hole is like that, 2-2. Or of a rotating black hole, the Kerr solution also has this 2-2 form. It's a very nice way of analyzing fields to see how these different principal null directions, as they're called, how they relate to each other. So that's a very quick thing you get out of it. And you don't see this at all easily if you write it in this tensor. So I'm showing you things which do work very nicely with the spinors. Now here's another thing that works very nicely. You see, remember for the Maxwell equation, you have a thing like this, very similar, but you've only got two indices. Now, what are the Maxwell equations in empty space? They're this. This D thing represents differentiation. It's what's called covariant derivative. It's the only thing you can write down when you see how does a thing behave as you go from point to point. How is its gradient? How does it change as you go around? And that's this differential operator tells you that. And you have this very simple equation. This equation is the equation of a massless spin-2 particle. So it tells you that gravity behaves like a massless spin-2 particle. If I had only two indices, the spin is half the number of indices. So if I had two indices, it would be a spin-1 particle. So the photon, if you like, satisfies the same equation, but with only two indices. And this equation you get for any spin. You don't actually have particles for higher spins, which have no mass, but if they did, they'd satisfy this equation. The neutrino almost has no mass, so it almost satisfies this equation. It's got a very, very tiny mass. And if it had no mass, you would have one index, and that would be the neutrino equation. So I always felt this a very attractive thing, which drops out of writing things in terms of spinors. Now, of course, all these things were written up very much in our book. And Wolfgang, I often would write things down, and Wolfgang would regard that as what I'd done as pretty obscure. He had a way of dealing with these things, which is called Rindlerization. He would Rindlerize my description and make it look nice and simple. He had a real skill in that way. And he certainly had these equations, and he had a way of making the thing look very beautiful and simple in ways which I had trouble doing. Okay, now that is this comes from what's called the Bianchi Identities. I remember giving a talk. I belonged to the same college as Dirac when I was a fellow at Cambridge. And I remember when I hit upon these things, I thought I'd like to discuss them with Dirac. And so I was sitting opposite him at a table at dinner. And I said, I'd like to show him something if he had some time. And so he said, that's fine. And we had a lecture room. And I wrote down this equation. And he said, where does that come from? And I said, it comes from the Bianchi Identities. And what was very puzzling to me, he said, what are the Bianchi Identities? Now, see, Dirac had been one of the leading people in working out the equations of Einstein and see how you might try to bring them into the scope of quantum mechanics, quantizing them. He was a leading figure in this. And I was very puzzled that he wouldn't know what the Bianchi Identities are. I'm sure he did know what them are, and I'm sure he worked them out himself. He just didn't know they were called the Bianchi Identities, which was quite a curious experience I had on that occasion. Anyway, these are equations just of the same kind that he was writing down when he was looking at particles of different spins. And you could see that this was the equation of a graviton. So I think he was interested certainly in what I was saying and hadn't quite looked at it in this way. So it was nice to be able to tell him something which was very close to things that he had done, and perhaps not quite something he had done. Okay, let's look at my next picture here. Well, you see now, if I may, the second volume, one of the topics is twistor theory. I want to give you a little bit of taste of twistor theory because it is where spinors sort of lead you somewhere. Remember, I had talking about light rays, and if you were to point a single point, then the spinors point along the light curve. So you can see how to describe light rays in terms of a single spinor. But what about light rays somewhere else? Now, can you describe them in terms of spinors in a nice way? It turns out, yes, you can. And the way you do it is you think of that light ray, and suppose here is your origin point. It's called X here, but let's make it an origin point. Then you look at that light cone, and you see where this light ray hits it. It hits it in a certain direction, and that direction gives you one spinor. So you've got one spinor for the direction of the light ray. I call that pi, because pi is really a momentum. You have to get it the right way around, and it's more appropriate, the momentum of the photon running along. And the other was the angular sort of part of this thing, which was how its angular momentum with respect to the origin. So there's another spinor, which is the one pointing along at the light. So think of the intersection of this light cone. You've got one spinor whose flagpole points that way, another one which points that way. And the two of them together give you what I call a twistor. And that's a way you can describe light rays in this very nice way. It works out very beautifully. Now, what's more remarkable is that I'll sort of jump ahead. It wasn't quite the way it came about originally. But if you think of this photon, not just a light ray, but think of it as a photon. And it's got a momentum, so it's got a certain strength to it. The momentum is a frequency, if you like. And it's got an angular momentum. And the angular momentum and the momentum together, you have to write it in the right way. And you get this object, which is this description which I'm giving you here. But suppose it has an intrinsic spin. If it's a photon, it does, because a photon has a spin about its direction of motion. You have to add that part in. And the intrinsic spin gives it another dimension. The number of light rays, when I say the number of them, how many degrees of freedom do light rays have? What is the big size of the space? It's a 5-dimensional space. So this is 5-dimensional. I tended to like things which are even dimensional because then they could have a chance of being complex manifolds. That the dimensions all pair off to be real and imaginary parts, roughly speaking. That's not quite so simple as that. And you have a complex space. So it would be nicer, particularly because how do you represent the point here? You see, I'm representing light rays over here by points. That point Z represents the light ray. How do I represent the point over here? Well, look at all the light rays going through it, and that is a sphere. That's the celestial sphere we started off with. That celestial sphere is naturally a complex sphere. In other words, it's a one complex dimensional thing. It's a conformal sphere, it's a Riemann sphere, it's a one complex dimensional thing. It's complex. So this space is almost a complex space. But to make it a complex space, you've got to add the spin of the photon. And then how do you see that structure here? Well, there is a way, and that is this picture here. The angular momentum of that photon is represented in this terms of this rather complicated looking structure. This is why it's called a twistor, because this is something which came from a description of certain kinds of electromagnetic fields that were found by Ivor Robinson, and he was working in Dallas, Texas, and he found these solutions of Maxwell's equations which had this very strange structure. And I thought they looked really interesting. And I remember this was a really miserable time because it was the time when Kennedy had just been assassinated. And I was in Austin, Texas, and Ivor Robinson and Wolfgang were in Dallas. And I had colleagues that I was working with in Austin at the time for that year. And I remember puzzling about these problems, and this awful thing had happened with the assassination. And in order to try and calm ourselves down, we made a trip down to San Antonio, and I think we went further, I can't remember exactly where. And on the trip back, well, the lady folk wanted to chat with each other. And I remember Krishna Oshvat had an otherwise empty car, and so I went back with him. And Krishna was not a very talkative person, so there were long silences. And during those silences, I tried to figure out what these solutions of Maxwell's equations were that Ivor Robinson had discovered. And I realized that they had this structure. They were like a light ray pushed into the complex. They were pushed in a rather subtle way. And they had, you imagine, not just the light ray, but all the light rays which met that light ray. Then you push it into the complex, and you can still see the light rays which meet it. And this gives what I call the Robinson congruence. And to try and understand it, we thought of this configuration. This configuration is what's called a projected Clifford parallels, or the hot vibration of a three-sphere projected. I won't go into the details of that, but you do have the structure representing how the light rays behave. And I found this interesting. And on the trip back from San Antonio, I began to count the number of dimensions this thing had. And it came out as 6. And I thought that's remarkable, because you make your light ray complex, instead of having 10 dimensions, which it would be if it was just straight complex, you only add 1 and it makes 6. This was very interesting to me for a reason which I'll rapidly explain to you. Perhaps I will. I had a blank here because I didn't know whether to stop here or not. Let me just say it. One of the motivations behind twistor theory was this. You see, when I was in Syracuse, as my first trip to US after being in Princeton, and I shared a room with Engelbert Schucking. And Engelbert Schucking told me that one of the foundation stones of quantum field theory is to split things into positive and negative frequencies. And the way you do this usually is by splitting things into Fourier components and did something complicated. And I didn't like that very much, particularly because I was interested in conformal structures, and the Fourier components don't remain. But then you have another description, which is you think of the Riemann sphere. This is the complex sphere. And now I have the real axis is the equator. And I'm putting -1 at the top and minus I at the top and plus I at the bottom. And infinity is around the back somewhere. And this is a Riemann sphere. And you look at your functions of positive frequency are the ones which extend into the top half, and the negative ones in the bottom half. So positive frequency is a nice thing to be able to describe in a geometrical way, because you're getting closer to talking about quantum field theory. So that was an idea I had there. And twistor theory, well, I thought you have something which splits into the 2 halves, which it does. And it does. Took a long, long time, years, before I realized it really does do positive frequency and positive negative frequency, because you have a clever way of representing Maxwell fields and gravitational fields and all this by doing things called contour integrals. They split into the top half or the bottom half. Not sure, I can't find it now. No, yes, these are the contour integrals. You have something with singular. I won't go into the details here. But what it is, and this is what took so long, it's not that the fields split into the 2 or bottom halves, but the cohomology does. And this picture represents cohomology. Okay. Obviously, I'm jumping a lot because I'm not explaining that. But if you want to know what cohomology means, and it's really the first cohomology describes these fields, and they're described by contour integrals. And these contour integrals represent the solutions of these equations. And that was this, that's it, these equations. And you get these for all the different spins, and you can solve all these equations in flat space very nicely using these contour integrals. It's a very nice way of using twistor theory. It uses cohomology, combines all these wonderful ideas together. These are, I should say, described in volume 2. And you will see the connection with this impossible triangle. It's something which locally makes sense, and the way it doesn't globally make sense is where the information resides. So that's exactly what's going on in a more sophisticated way. Something locally makes sense, and the discrepancy with it making sense globally is contained in this contour-integral, which describes the field, describes the massless field, and this is one of the big cornerstones of twistor theory. I've just been rambling, I'm afraid, on in lots of things which are in the book, and there are starts in a very sort of simple way, although I'm learning to add two twistors is not two spinors is not really a very simple thing, but nevertheless, and it goes off and talks about twistors in the second chapter, and the things that I've described are all in the books. And when you look at the Rindlerized version, you'll see a lot easier version than probably what I've been describing you to here. So it was a great honor to be able to work with Wolfgang and to collaborate on these books. We do talk about the abstract indices very much. We do, in fact, in the appendix, in one appendix, we talk about the diagrams, but the diagrams don't feature strongly in the book, but nevertheless, the abstract indices do. And if you want to talk about spinors in space-time, you really need the abstract indices. It makes life so much simpler. And it's often tensors themselves are much more easily handled in that way too. I'm sorry to have probably gone on too long, but thank you very much for listening. And I hope I've been able to give some idea of what we did together. And I should say, Wolfgang was an absolute delight to work with. We often collaborated together. That was the best. Sometimes we were distant, probably in different continents, and then we would usually do it by post. In those days, that's what you did. We didn't have email, and the letters were a great joy to have. When we were together, it was more fun, and we talked about lots of things, not just spinors and space-time. He was a very charming person, and I remember also learning lots from him about cosmological horizons, which had a big effect on the ideas I had about cosmology later. So let me end by paying my respects in this way to Wolfgang, a wonderful friend, a wonderful colleague, a delightful person. Thank you very much.
Thank you very much, Sir Roger, for a wonderful presentation. For those of you who have questions, you can type them in the Q&A, but before we go to the questions, I'd like to hand the reins off to Linda Rindler, who'd like to say a few words of thanks.
Indeed, I would. It is my honor and pleasure to express our enormous thanks to Roger and to the University of Texas at Dallas for this extraordinarily special event. The cornerstone of UT Dallas's genesis in 1969 was a commitment to excellence in the area of natural sciences and mathematics. Today's presentation by Sir Roger Penrose is an example of how the university can be identified as a national research and education champion. I am once again so honored to have been able to hear Dr. Penrose share fascinating pieces of his work. And certainly I wish to share a special word of gratitude for recognizing Dr. Wolfgang Rindler. Please allow me also to acknowledge the others, the wonderful presenters from UT Dallas, Dean David Hyndman, Dr. Dennis Kratz, Dr. Mustafa Ishaq Bushaki, Dr. Mohammed Akbar, and Dr. Anvar Zakidov, brilliant minds who exemplify the strong and collaborative leadership of the School of Natural Sciences and Mathematics. Thank you so much.
Well, thank you very much, Linda. Lovely to see you too.
Thank you.
Thank you so much, Linda. So we do have some questions. I know we're tight on time, but for those of you who can stay on, feel free. So we have a question from Alexandra Brosius. What is the distinction between a spinor description of space-time and a space-time as a manifold with spin?
But the spinor description is really a description. It has to be what's called a spin manifold in order for spinors to exist globally. And they always exist locally, but you may find when you go around and come back that your spinor has become its negative or something, which is a restriction on the space-times. But it's not much of a restriction. I should say that spinors, as described here, are not a thing to be recommended, I think, when you're going to higher dimensions. It's something very specific to low dimensions, that where you see this, the dimension of the spin space goes up exponentially with the dimension of the space-time. So they get more and more complicated with lots and lots of internal relationships. They're very, very handy, useful for space-times, which have 3 space and 1 time dimension. When you go up, then, although people use spinors, they're not really a contender for things that you'd want to use to do your calculations. But I think the answer to the question is that a space-time with spin structure, if that's what you say, I'm forgetting exactly. I think if you've got a space-time, you're very close to having a spin structure. I've gone a bit rusty on the details here. But
okay. Well, there's a second part to the question, which you somewhat touched on, and that is, can spinors be manipulated to describe black hole spin?
Well, certainly. For example, the Kerr solution, there is something which I did with a colleague, which you can certainly use spinors for, where when you look at the polarization effects of the spin of a black hole on the polarization of a photon, which goes whizzing past it. And there is an invariant that you get from this, which I did with Martin Walker. And these are things which are not at all easy to see in terms of tensor descriptions. Certainly the Schwarzschild solution, the weak field limits, you see, well, I should confess that there is a problem which has haunted twistor theory for a long time. This is not spinors. I should retract a bit. I think you're talking about spinors, aren't you? Not twistors.
Yes.
And spinors, well, I should say Chandrasekhar wrote his book on black holes, and it's full of spin coefficients. Now, these are really spinors when you're interested in taking the components as well. You're not using them in an abstract way so much, but you're actually using spinors. This is work that I did with Ten Newman particularly, where you use the components of the spinors. You can do it without using spinors, but it's more direct, and you can see why you're doing it when you use spinors. And these are spin coefficients. And when I had my picture of the relationship between the spin frame and very early on, and the 4-vector frame, that's exactly what you're using. You're using the spin frame to determine the various parameters, whether like rotation coefficients, but they're spin coefficients. And they simplify a lot of calculations. And this was what Chandrasekhar used in his book. So it's absolutely full of spinor techniques there.
Excellent, thank you.
And that's talking about the perturbations of black holes and that kind of thing. So it's a very fundamental piece of work.
Terrific. So I have a question from Earl Jennings. What is the theoretical objective of quantum mechanics as it relates to quantum field theory?
Quantum mechanics is related to quantum field theory. Well, quantum fields, you see, quantum mechanics is when you're looking at an individual particle or something. You see, when you're talking about fields, if you want to talk about the electromagnetic field, you have an indefinite number of particles. And so you can't, quantum mechanics is when you've got a definite number of particles, and you can, you have a finite dimensional vector space. But when you're talking about things like, say, the electromagnetic field, then that's where quantum field theory comes in. But I don't know. I mean, splitting things into positive and negative frequencies is a crucial feature, certainly in quantum field theory.
Okay.
I mean, I thought for a moment you were going to ask me about quantizing gravity, which is another kettle of fish altogether.
No worries. So I have a question from Juan Ortega. Why in the light cone representation is the present portrayed as a node or singularity?
Ah, no, that's a misleading. Maybe I was not being clear. I'm talking about a single event in space-time. It's only one point because it is localized both in space and in time. The pictures where I had these horizontal planes going across, that's more. You see space is a three-dimensional plane going right across the picture, which of course to draw it, you might draw it as a two-dimensional plane. But that is now, if you like. But an event, as it's called, would be one point. So no, you don't think of that point as space-time, as a space. That's not space. That's space. That's an event.
Okay, excellent.
In a technical sense.
Question from Don Black. What is the relation between spin and mass, or spin and space-time warp?
Oh, well, it's not really directly. I mean, mass and spin are two different things. We were just talking about quantum field theory and things like that, or particle physics. There are two things which are absolutely conserved if you have what's called the Poincare group, which is the group of special relativity. If you have special relativity and the group of symmetries of that, then you have these two numbers, which were called Casimir operators. And these are absolutely conserved. And these two numbers are mass and spin. Now, they're not the same, they're quite different. And a particle can have a definite mass or it can have a definite spin. And they're unrelated to each other. The spin has to be an integer or a half integer. The mass can be anything. Well, we don't know. Maybe it has to be restricted in certain ways that are unknown. But
okay. So I have a question from Da Feng. Why is geometry so important in all you do? If humans did not invent geometry, does that mean we could not make such progress in physics or science in general?
Well, geometry is a curious thing, and it's very individual in the sense that some people like to write down equations and some people like to play with geometry. I'm much more a geometry person. Chandrasekhar was much more an equation person. So he could judge from an equation, whether it had a certain beauty in it and was likely to be useful or to be correct or something. I would not have that skill so much. I would be more, my own skills would tend to be more in the geometry. So it's not a universal thing. And I certainly found when I was growing up as a mathematician that the biggest divide between the way people thought was in how geometrical they were. And the geometrical ones were in a minority. I think the minority had to do, there's a sort of selection effect, that it's much harder to set exams if you're a geometrical thinker. And I found this myself when I did my undergraduate degree at the University College in London. I found out that my best paper was actually in algebra, not in geometry, even though I thought of my skills are particularly geometrical. That is because when you try to solve an algebra problem, you can sort of do the algebra and write down the answer. That is the answer. But when you solve a geometry problem, you've got to translate that into, you see how to solve it, then you translate that into the language, and then you write an essay more or less about it. And my writing was slow, and I didn't, you've got to use one part of the brain to solve the problem and the other to write the essay or whatever it is. And I found that more tiresome. So I find that it may be harder to examine geometrical problems. And that's probably, in a way, why you tend to find that the people who do well in the exams are more or less geometrically inclined. I think the ones who are very good on the whole are good at both. And so you find that a geometrical talent is very useful if you're a real research mathematician. But even then, there's a clear division. You find those who are good analytically, are good at thinking about numbers, number theoretical people, or algebraics, not quite the same skill, algebraic skills. And the ones who think in pictures more, which such as myself, it's a bit different. And I wouldn't say it's a universal thing.
Excellent, thank you. So we have a question from Gary Evans. What was your most exciting discovery and or insight, and what immediately led to that experience?
Oh, that's a difficult one. You see, I think that the Twistors thinking of that was one of them. So that was certainly one of them. Let me give you another one because it's hard to say. The other one was this idea I had in cosmology, which was, well, there's several ideas. There's the thing that got the Nobel Prize, I suppose I should mention, but let's mention the cosmology one. I've been worrying about the difference between the Big Bang and the singularities in black holes. And you see, I've been working on black holes, and you get this kind of curvature, which is the spiral curvature, as I mentioned, and it seems to diverge and become the dominant thing in the black holes. Whereas in the Big Bang, we've also got a singularity, but it's the other way around. And this Weyl curvature, this particular kind of curvature, which describes the gravitational degrees of freedom and the distortion, I was trying to describe that in the talk, seems to go to zero. So it's very, very different. And this difference between the black hole singularity and the ones is infinity, the ones at the Big Bang and the ones in black holes just seem to me extraordinary. And I, for a long time, just postulated for no good reason that for some strange reason, quantum gravity had to make the ones in the black holes be different from, I have to be some very strange kind of theory. But then I had this idea which had to do with thinking about the very remote future. And you see, we have this thing called dark energy, which I don't like the term because it's neither energy nor dark. But it's actually most best described in terms of this cosmological constant that Einstein introduced for the wrong reason I guess, a couple of years after he introduced general relativity. It's the only thing you introduce it without changing the theory radically, a thing called a cosmological constant. And it seems to be there. And once I got used to the idea that it was there, I had to struggle with not liking the idea initially. And I knew what infinity looked like when it was there. This, I should say, was from stimulation from Wolfgang Rindler, because when I first started to think about the structure of infinity, the conformal structure of infinity, was to understand Wolfgang's work on horizons. And he'd written this fundamental paper on the difference between particle horizons and event horizons. And cosmologists were extremely confused by these things. And Wolfgang's paper made it absolutely clear. And I remember I was traveling to the United States, the first time I'd ever done this on a flight, and I was going to see what Wolfgang's paper's influence was on the things I was thinking about. And I remember looking out the window and seeing that the wings flapped. And I thought, I didn't think airplanes' wings were supposed to flap. Birds' wings were supposed to flap. But fortunately, there was free alcohol on the flight. And so I could calm myself down and look at Wolfgang's paper. And then I realized the difference had to do with whether it was the past infinity was space-like or the future infinity was space-like. And one had to do with the particle horizons and the other had to do with the event horizons. And it made it all clear to me. So that was a big step. But the thing I was coming to was the realization that infinity, because I was thinking, what happens to all the black holes? They evaporate away by Hawking evaporation. And there's nothing much left except photons. And I just thought how incredibly boring this is for the whole of eternity from then on, this unbelievably boring universe with nothing in it but photons. But then I thought, who's around to be bored by this? Just photons. And photons are very hard to bore, not just because they probably don't actually have experiences, but because the passage of time is 0 for a photon. And they reach infinity in no time flat. So they go right through infinity and they see what's on the other side of infinity. And I thought, well, what can be on the other side of infinity? Maybe it's another Big Bang. So I had this idea, and it sort of made sense that this very, very cold, very rarefied remote future could somehow be like the very, very hot, very, very dense Big Bang, so long as there is nothing there with any rest mass, such as photons. And then they don't register the size of the universe. They only know the conformal structure. So the idea was that if you have either the remote future, when it's mainly just photons running, well, there's a bit of extra, but forget about that for the moment, or the Big Bang, where it's so hot that things are moving around so fast that the rest mass makes not a hoot of difference. They're more or less massless. Everything is massless at the Big Bang. So you've got massless at both ends. Massless things don't know big from small. They're just interested in the conformal structure. So this very rarefied, cold, remote future behaves physically just like, if you've got only massless things, a very hot and dense Big Bang. Crazy idea, absolutely crazy, but it seemed to make physical sense that you could match the Big Bang onto the remote future of a previous eon. And our remote future will become the Big Bang of another eon. So this was my scheme idea I had, I don't know, 15 years ago, longer by now, I think. And even now, one is even beginning to see observational implication of this, which some of them seem to be making sense. So that had to be a decent idea if it turns out right.
Wow. Thank you for sharing that. Fantastic story. So we are well over our time. We have so many questions that are remaining and parts of questions. But with that, I'd really like to thank you. It's been a real honor to host you. And thank you for sharing your connections with Wolfgang and UT Dallas. Thank you all for coming today. And please give virtual applause for our terrific speaker today. Hopefully we'll have an opportunity to do another one of these in the future, and hopefully you could actually come over and give it live here at UT Dallas. Thank you very much.
Thank you. Thanks.